this video, we are going to see a problem based on continuous time Fourier series. Here is the problem. We have to obtain Fourier series coefficients for the following waveform. The waveform is given like this. Something like this, we are having a waveform, and for this we need to obtain a Fourier series coefficient. And Fourier series coefficient can be obtained if we get a complex form of a Fourier series. So in other words, what we have to get is a complex form of Fourier series for this particular waveform. So in a complex form also we need to get a coefficient, and that coefficient is obtained if you decide a one cycle of the waveform. So one cycle in this particular waveform will be like this. Because this particular part is repeating itself. So let's take down this one cycle. Here it is minus t by 2, and this is plus t by 2, and this is some constant minus t1 and t1, and over here we are having a origin. Drawing a separate cycle is very much essential, because from that cycle we can write an equation of the waveform. So if I consider this, the symmetric waveform I am obtained, and x of t I can very well write equal to 1 and it is equal to 0. So 1 I am getting in this interval. I can easily say mod t is less than t1. So if a mod t is less than t1, during that interval waveform is having a value 1 and it is 0 in remaining interval. So remaining interval will be t1 less than mod t less than t by 2. So this particular waveform now converted into equation, and over here important point is that for this particular cycle I can say the time period is capital T. And how to obtain that? It is quite simple. The upper limit is t by 2 and lower limit is minus t by 2. So it will be t by 2 minus t by 2. So if we solve, we will get a time period is capital T. So if a time period is capital T, I can get a fundamental frequency. omega 0 nothing but 2 pi upon fundamental time period, which is capital T. So this is the most important part we are getting. Now we can proceed further for writing a complex form of a Fourier series. So any signal x of t with a time period capital T can be represented in a complex form of a Fourier series in this manner. X of t equals summation k from minus infinity to infinity a suffix k, it's a Fourier series coefficient e raised to j k omega 0 t. So in this ak is nothing but Fourier series coefficient. And how to obtain this? Ak is nothing but 1 upon time period, integral over that time period, x of t into e raised to minus j omega 0 t into k dt. So this is the formula which we need to use in order to get a Fourier series coefficients. Let's apply this formula to the waveform that we have defined. So this is a waveform we are having. So time period is t only. So I can say now ak equals 1 upon t integral. Now the waveform exists from minus t by 2 to t by 2. So the integral will have the limits minus t by 2 to t by 2 x of t into e raised to minus j k omega 0 t dt. Now, being a symmetrical waveform, we can cut short the limits like this. So I can say now ak equals 1 upon t. First we will check the waveform exists from minus t1 to t1 because the remaining interval it is having the value 0 as we defined. So I can say over here now ak as 1 over t minus t1 to t1 and the value of the waveform is 1. So no need to mention 1 getting multiplied with e raised to minus j k omega 0 t dt. Now we have to solve this integral. So ak equals 1 by t. Integral of this is e raised to minus j k omega 0 t upon minus j k omega 0 and limits are minus t1 to t1. So ak we will get as, see all this thing constant I will take outside, so minus 1 upon j k omega 0 t and let's apply the upper limit e raised to minus j k omega 0 t1 minus, if I apply the lower limit it will be j k omega 0 t1. Now I will adjust this minus term so that ak will be 1 upon j k omega 0 capital T inside bracket e raised to j k omega 0 t1 minus e raised to minus j k omega 0 t1. Now we know Euler's identity. For that purpose, I will adjust 2 in the numerator as well as denominator, and I will take this 2j inside the bracket so that ak will be 1 upon k omega 0 t. I'm adjusting 2. So first I will multiply in the numerator and e raised to j k omega 0 t1 minus e raised to minus j k omega 0 t1 upon j2. So we know by Euler's identity, e raised to j theta minus e raised to minus j theta upon j2 is nothing but sin theta. So here this term is theta. So I can say now ak is nothing but 2 upon k omega 0 t multiplied by sin theta, where theta is k omega 0 t1. Now we know in the first place what we have decided or what we have calculated omega 0 as a fundamental frequency, nothing but 2 pi by t. So let's substitute over here. So since omega 0 is 2 pi by t, a fundamental frequency, if we substitute, we will get ak as 2 upon k multiplied by 2 pi by t multiplied by t sin k multiplied by 2 pi by t multiplied by t1. So doing so, what we'll get, t get cancelled, 2 also get cancelled, and in the end we will get ak as 1 upon k into pi multiplied by sin 2 pi by t into k into t1. So this is a general form of a Fourier series coefficient. Now the problem is that over here this is valid for k minus infinity to infinity except k equal to 0. Because if I put k equal to 0, this is 1 upon 0, this is sin 0. So in the end we are getting an indeterminate form. So in order to avoid that, what we will do, wherever we calculated ak in this formula, so all the discrepancies we will calculate. That means I will calculate a0 by using this equation as it is. So if I put k as 0, I will get a0 as we are going to use this equation. So we are putting k equal to 0 in equation which says ak equals 1 by t integral minus t1 to t1 e raised to, if I put a 0, so obviously it is e raised to 0, but here we are using a generalized term. So generalized term is minus j k omega t dt. So in this equation we are putting k as 0, so I'll get a0 as 1 by t integral minus t1 to t1 e raised to 0 dt. So it's a simple integral which says 1 by t and e raised to 0 is nothing but 1 whose integral will be t and limits are minus t1 to t1. If we simplify, we'll get t1 minus t1, which is 2 times t1. So I will get a0 as 2 times t1 by t. Now our answer is complete over here. So by selecting the values of t1 as the ratio of capital T, we can plot it. Meaning, let's try out for one ratio. So we will consider first ratio where capital T is 4 times t1. It's just a random ratio we have selected. So this implies what? t1 by t is nothing but 1 by 4. So if you use this ratio over here, we will get AK as 1 upon k pi into sine 2 pi into k into 1 by 4. So this further simplification will give us AK as 1 by k pi into sine pi by 2 into k. So we will get this particular Fourier series coefficient for the substitution capital T equal to 4 times t1. Obviously this is not true for k equal to 0. So what will be a0? Simply wherever we got a0 over here, t1 by t we will put as 1 by 4. So a0 will be 2 multiplied by 1 by 4. Again simplification will give us a0 nothing but 1 by 2. Now let's plot this for different values of k. Remember k is an integer. So let's plot ak. Which is nothing but a Fourier series coefficient. We are going to plot AK against the values of k, where k will be 0. So when k is equal to 0, we will get this as 1 by 2. So somewhere here we will have the signal, which is a0, nothing but 1 by 2. Now, if I put k equal to 1, so which is the sine pi by 2, and sine pi by 2 is 1, but k is equal to 1 over here, so it's basically 1 upon pi. So for k equal to 1, it will be 1 by pi. So somewhere here we'll get the signal. Same will be true if I have k as minus 1. So if k is equal to minus 1, sine minus pi by 2 is nothing but minus sine pi by 2, which is minus 1 in the end. And k is minus 1, so that minus will get cancelled in the end. For k equal to minus 1 also I am getting a same value, which is 1 upon pi. K equal to 2. So if I put k equal to 2, I'll get a sin pi, and sin pi is 0. So k equal to 2, I will get the signal 0. Same is the case for k minus 2, we will get signal as 0. Now for 3, if I put k equal to 3, sin 3 pi by 2, which is minus 1, and k is 3, so it's minus 1 by 3 pi. So for 3, we'll get signal somewhere here, which is minus 1 upon 3 pi. Same will be the case for k equal to minus 3. So k equal to minus 3 also, we are getting minus 1 upon 3 pi. So if I see properly over here, for even numbers from 2, 4, 6, 8, this will become 0. So signals will not be present for k equal to 4, k equal to 6, similarly over here k equal to minus 4. But if I have k equal to 5, it will be there, and the value will be 1 upon 5 pi. Similarly for k equal to minus 5, it is 1 upon 5 pi. So thing is that for all odd numbers, you will get a signals present alternately plus and minus, the way we got for k equal to 3, k equal to 5. So this is a plot of a Fourier series coefficient if I have this ratio t1 by t as 1 by 4. Let's further elaborate by taking the ratio now t equal to 8 times t1. So let me write here, it's a plot of a Fourier series coefficient. For capital T, it's 4 times t1, and this is a plot of ak versus t. Now we are having a plot of Fourier series coefficient where the ratio we are taking t as 8 times t1. So let's take the general form of AK, which we obtained over here. Now what we are going to do, we are going to put capital T as 8 times T1. So AK will become 1 upon K pi into sine 2 pi by 8 T1 multiplied by K multiplied by T1. T1 get cancelled, and in the end we will get AK as 1 upon K pi into sine pi by 4 into K. Obviously, it's not true for K equal to 0. We need to find out A0, and A0 in general form it is 2 times T1 by T, which is nothing but 2 times T1 upon 8 times T1. So once again T1 get cancelled, and we will get A0 as 1 by 4. So let's plot it quickly. For plotting, let's not find out the values for each value of K. Simply we will decide this will become 0 if I have K equal to 4, K equal to 8, K equal to 12, So it's in a multiple of 4. If I put k values, I will get a signal equal to 0. For rest, it will be there. Meaning, if I have k equal to 2, it will be sine pi by 2, which is nothing but a 1. So considering this in mind, we will get a plot of AK like this. So for k equal to 0, it is the value 1 by 4. For k equal to 1, it will have some value which is sine pi by 4 upon pi. So it will be less than 1 by 4. So k equal to minus 1 also you will get the same value. K equal to 2, k equal to 3, and the most important part is k equal to 4, it will be 0. And beyond 4, if I have the values, you will come to know the values will be negative. Means it will have the nature like this. So for 5, it will get a negative value, 6, 7 also, and most importantly for k equal to 8, it will be 0 because it's a multiple of 4. Same will be the case in a negative direction as well. So what we have observed over here is that we are getting more samples if we have a time period t1 which is very less compared to a capital T. So in the previous case what we have, capital T as 4t1 and now we have capital T as 8t1. See the difference that we are obtained. Here we are having only 3 samples, or from here to here we have 3 samples with 2 zeros, but here if I have a time period very small, I can get a maximum number of samples. Same will be the case if I have a T 16 times T1 and all that. The thing is that as we keep on decreasing the time period, the frequency will increase and more samples we can get in the plot of AK. Thank you.